Good morning. Okay, today I'm gonna talk a little bit about assignment two, just a few questions. What I've done this time, which is a little bit different from the first time, is that I have uploaded a video to Canvas with the solutions for the learning and reinforcement, but I've also put a solution PDF on there. So if you don't want to watch the video, you can just look at the solution PDF. I noticed the video was getting pretty long because I was going through each of the learning and reinforcement questions. It was 27 minutes. So asking you to watch that to get the solutions just seems excessive because that's not part of lecture time. So the solution PDF is there for you to get a quick glance at things. And if you want a further explanation of the questions, please watch the video and you can just skip to that question. So that way you don't have to watch the whole thing to get the answers. Um, I'll talk about the extension questions like now instead of in the video, but the written solutions are in the PDF. Then we'll talk about the test guide today, and then we'll go into the actual lecture. So there were two of the learning and reinforcement questions I just wanted to point out, mainly as a reminder. The first one was 1F. So this is out of the ones I've seen so far where there have been some issues. Just a reminder that with elements, when we ask if something is an element, we're asking if this entire thing on the left side, that one whole thing as an object, is an element of whatever set is on the right. This means that we need to see this entire object in that right set. So in this case, this is false because we don't see the set containing W with the set X as one object. We just see W as an object and we just see the set containing X as an object within the set. So those are two separate things in the set compared to this giant singular object on the left that we're asking about. So that was one mistake that I saw a couple people make just out of the few submissions that were in before midnight last night. Um, two was done really, really well. Three was done surprisingly well. Four, I didn't really see many issues with four either. And what I'm about to say about 4B is also not a complaint. It's just sort of a preamble for the test. And it's because I didn't make any real specifications here on the assignment. So 4B, whenever we say something like explain by mentioning reflexivity, symmetry, and transitivity, uh, and I'll specify this on the actual test as well, it's good to always provide specific examples when something is, say, like not reflexive. So in this question, you could say it's not reflexive. And what most of you did was say, because nobody can be louder than themselves, which is fine, because in natural language and in the real world, you can't be louder than themselves. But this question asks about the equivalence relation in siblings. So this is a specific circumstance. So it's better in this case to give specific evidence and say it's not reflexive because, for example, we're missing Kiko, so not every element in our set is louder than itself, something like that. So there's a specific example that's missing that shows it's not reflexive. So you weren't docked any points on the assignment for not doing that because that wasn't part of the instructions. But on the test that's coming up, I recommend giving a specific example, and I'll point that out in the question. And I mentioned that just because it asks about a specific scenario, a specific universe. Okay, so I want to talk about this question. This question was done really well from what I've seen. So the idea was to create simple sentences for question A, and then for question B, just put like a not in front of them, either in the VP or right before the noun phrase. So the sentences most people came up with was something like he swims or he swims quickly or some variation of that. And then for the dog example on the right, like it is an animal, it is a dog, it is a Shiba. If you did something more complicated, that's fine, but this is really uh, all you needed to do to get an answer to this question. And for both of these ones, it was uh, upward entailment. So if you have something specific, you're entailing something general. So if he swims quickly, then obviously he's swimming. If you have a Shiba, then obviously you have a dog. But the other direction doesn't quite work. If you swim, you might be swimming slowly. It doesn't guarantee you're swimming quickly. And if you have a dog, then you don't necessarily have a Shiba. You could have a Dachshund. Yeah, you'd have to do it for both of them because it's not necessary that VPs and NPs work exactly the same. So each example was independent in this case, but they both happen to work out the same. So for the adverb phrases and for the NPs here, these are both case of upward entailment. And what we found when we negated both of these, so when we made them doesn't swim and not an animal, the direction of entailment reversed. So what we got here was now downward entailment. So you could use basically the same sentences. So I can just use uh, technology to say he doesn't swim. It's probably faster if I just type it out again. And he doesn't swim quickly. And now this changes. So if he doesn't swim quickly, that doesn't mean that he doesn't swim. It just means he doesn't swim quickly. He could swim slowly. But if he doesn't swim, then you know he doesn't swim quickly. So in this case, the general case, or the fact that he's not doing the general case, entails that he's not doing the specific case. So there you have downward entailment. Similarly, with the dog example, it is not a dog is going to entail that it is not a Shiba. Since if it's not a dog, it can't be a Shiba. But if it's not a Shiba, it can still be a dog. Sorry, yeah, if it's not a Shiba, it can still be a dog. It can just be a Dachshund or a Corgi or something else. So in this case, you have the negated general entailing the negated specific. So this is downward entailment. So basically, when you negate them, the direction of entailment changes. So that's what was happening with that question. And although this wasn't asked in the question and this wasn't up on the forefront, this was another push at the differences between entailment and presupposition. Because with entailment, we see there's a change. When you negate a sentence with entailment, the entailment changes direction here. But if you have a presupposition and you do an attitude test, you're not getting the same thing happening. A presupposition is still going to remain the same. So hopefully this exercise also sort of reinforces the differences between entailment and presupposition. So when you revisit that and study for the test or review those older exercises, those differences sort of stand out again. If you gave more complex sentences, I mean, you should have come up with the same thing. I'll see your individual responses though. If something happened and you used quantifiers and things got too complicated, again, these are understanding and extension questions. So if you went off in a weird tangent world and ended up answering something way more complicated than you need to, I'll take that into consideration since it's really just more about exploration than it is necessarily getting this 100% correct. I mean, I still want you to answer these questions, but if you made it way too hard for yourself, I'm sympathetic to that. The last one. Okay, this one was a little bit more cryptic, I think. But overall, from what I've seen, this one was answered as well. So this was about inferences. So there was an exchange between two people here. I gave you a little hint. I said, focus on this line and what sort of inference was used here. So to explain this, the company had an account there for 6 months. And sorry, let me rebox that. I boxed the wrong 2 lines. Do you have any bank accounts in Swiss banks? No. Have you ever? The company had an account there for 6 months. So when the defendant says the company had an account there for 6 months, this is done intentionally. Basically, he's trying to not answer the question directly about himself. He's implying something. He's trying to get the implicature across that I never had an account there. He's saying the company had an account there to make this implicature that I never had the account there. That's what he's saying. But the jury inferred something else. The jury inferred that he said, I had an account there. So when the original sentence was made, the original verdict, based on this line, it was, okay, you're guilty, you had an account there. So when the US Supreme Court acknowledged this, the claim that they made, which was written here, was that it's the responsibility of the questioner to press for further information when the respondent is unresponsive. So what this means is that they understand that this was an implicature. This was just based on expectation, that the defendant did not actually give enough information here, and that the questioner just assumed that what was said was, I had an account there. And they made an assumption about what actually happened rather than pressing for further information. So the overall idea is, first of all, what type of inference was it? It was an implicature. And was it logically justified for the acquittal? The answer here is yes. And the answer why it's yes, in terms of the law system, and I'm no lawyer, so I'm not 100% picky about this, of course, and I don't expect, none of us are lawyers. But because it's based on expectation, the law is not based on expectation. It's based on facts and confessions and evidence. So if the defendant admitted in real words and gave hard evidence and facts that he did do it, and sure, the original verdict is fine. But because the original verdict was based on this implication, on this implicature, based on expectations rather than fact, the original verdict wasn't really logical. So to override this would be understandable and logical by the Supreme Court. So that's sort of the idea of this question. I believe I heard some voice.
If we answered no to the was it justified, and if we gave enough evidence to support our opinion, will you make it right as well?
Yeah, yeah. As long as you have some sort of justification for it. Again, these questions are more about thinking. Like the point here was implicature. That was what I was going for. Like that's the core mark. Like that's 1 out of 2 points. And then the second point is, was it justified? So yes or no, and then your opinion. And as long as your opinion backs up your yes or no, that's your other point there. So the goal of these understanding and extension questions is usually it's part linguistic, it's part, work with the material, think about the material, get it as right as you can within the context of the course. And then there's also some points there, for your effort, for your attempts, and for just thinking about things. So it's not always 100% about did you get it completely correct? Because I know these questions are sometimes hard and sometimes cryptic. So I don't want to put an absurd amount of pressure on you getting these completely correct all the time. Okay, Were there any questions about this assignment that I didn't cover now that you desperately want to go over or have, or not even desperately want to go over, just want to talk about before I talk about the first test?
Can we go over number for predicate notation?
Predicate notation, yeah. So this is just about putting things into words. So there was a slide where I talked about how to treat intransitive, transitive, and ditransitive verbs with relations. So this is very similar to something like loves, where we say in English, we can frame a sentence as X loves Y, for example. So this is an example of a transitive verb. So when we write this as a relation, we're looking for pairs of things, so subjects and objects, X and Y, where X loves Y. So what we do here is basically we're looking for a pair of subject and object, and then we have the sentence frame in the description. So for this example, with louder than, we're looking for pairs of subjects and objects, X and Y, where X is louder than Y. And that would be an example of predicate notation for this question.
Is it necessary to put the like X and Y included in siblings?
You can if you want, but that's not something I require. But to be
Okay.
complete, that would be good to include. But because of the context of the question, it's understandable where it's coming from.
Okay, thank you.
Okay, I'm going to briefly talk about test 1, which is next Tuesday, so it's a week from now. This is on Canvas, so I'm sure some of you have seen it, some of you haven't. It covers lecture 2, 3, and 4, and you can do it anytime between 9 a.m. and 9 p.m. So once you start it, there is a time limit, but you have freedom in when you start it. So you can do it during class time if you want, and I will reserve the 60 minutes of class time to do it. So I'll be in Zoom, but there's no lecture. That way, if you have questions during the test, you can ask them and I'll be here. That way you don't have to worry about email. It'll be 60 minutes for it, and I'll talk about some extra little time stuff that goes on. So the person who's doing the captions for this course, you don't have to worry about being here for the first 60 minutes. If you don't want, feel free to take a break next Tuesday. But there is a lecture after that, so that'll start at 11:35 a.m. So it's 10%. It is open book, open note, open assignment. Use whatever you want. Just do it by yourself. That's the only request I have, is that you do it by yourself. There are 3 main questions, so I just sort the questions by lecture topic for this one. So there's one big question for inferences and semantic relations. There's a set theory question with 3 parts, and there's a relations and function questions with 3 parts. And basically, the test is just a taste of all the assignments and a much smaller version of it. So for inferences and semantic relations, there will be 2 pairs of sentences. It's either entailment, implicature, presupposition, or none. You just have to get one of them, even if there are, like, say, entailment and presupposition. You just have to choose one of those if there are one. And you're only doing inferences from A to B. You're not doing both ways. It's just A to B. Use either contradiction, reinforcement, or attitude tests, and you don't have to show all the tests, just the ones that work. So that'll be typed in directly to Canvas. So you know what the question is, you just don't know what the sentences are. And that'll be, there's different variants of all the questions, so you might not get the same question as your friend, but they're all about the same difficulty. For set theory, you'll have a couple true false questions about sets, elements, subsets. So a lot like question 1 on this assignment. You'll have to list some elements and list notation. That's a lot like question 2. And there will be a very short set law proof. And when I mean short, like 3 to 4 lines. That's it. It'll be very short. For the third question, relations and functions, you'll have to list the elements of a relation. So again, a lot like question 4 on this assignment. Uh, you'll have to state whether the relation is an equivalence relation. So a lot like the symmetry, transitivity, and reflexivity. Question 4. And then the last one is a function onto and one-to-one. And if not, just a short explanation of why. So a lot like question 5. So as you can see, the tests are just very similar to the assignments. The difficulty is going to be the same as the assignments. It's not going to be any harder. The only difference between this and the assignments is that one, it's shorter, but there is a time limit when you do it, and you have to do it by yourself. So a little bit of pressure, but again, like I said at the beginning of the course, the tests are not here to be like this tough wrench in the head that is supposed to be stressful and make everything painful. It's just here to make sure that you understand the basics of the course and can do it by yourself under a little bit of time pressure.
I have a question.
Yes.
So for number 1, inferences and semantic relations, if there is both, like for example, both implicature and presupposition, we only need to state one.
Yeah. So if it's both, usually it'd be entailment and presupposition, but if it is both, you just have to show me one of them.
And also, did you say we also have a lecture that day?
Yeah, so that's a 2-hour lecture day. So the test is only 60 minutes. So it'll be a shorter lecture. It'll only be about 40 minutes long, but it will be from 11:35 to 12:20 on that day. And I mean, if things are, if you're exhausted after the test, of course, just watch the video after if that's something you prefer. My intention is not that this test is exhausting. That is just sort of uh if you've done the assignments and you've done the practice questions, it should be not stress-free, but it should be straightforward-ish. Do you suggest us to write the test during the free period given to us? It's up to you. If you're here every week during the live lecture, sure, do it during that time. But if you are not someone who takes tests during the mornings, or if your brain's not active, or if you have freedom during the night and you think you're a better test taker at night when you have a better or more quiet time, then take it later during the day. I'm giving you that time so that way you can choose to write it during a time when you have the most freedom and when you feel like it's best for you. Okay, so uh, there's some stuff. I want to talk about the time policy. It's a 300 level course, so I don't actually care that much about if you go over time a little bit. Canvas is going to auto submit your test after 60 minutes, but I know there are technical difficulties you might have. I know some people like to check over their answers and take a little bit longer than others. Sometimes there's a question you get stumped on or your brain blanks out. So you can submit your test over email to me up to 45 minutes late, and that's completely fine. You can still get 100%. I don't need an explanation why. Um, Canvas will not accept it 45 minutes late, but just email it to me. There's no penalty. You don't explain anything, so that's fine. The reason I'm not just giving you 105 minutes on Canvas is that by the end of the 60 minutes, I want to make sure that you've seen all the questions and have worked on the questions a little bit. If you haven't seen all the questions and worked on them by that point, uh, you may be running into troubles just in terms of knowing the course content, and you may be relying a little bit too much on resources rather than understanding. So by the time that 60 minutes is up, you won't be able to see the questions anymore. So please make sure that you do have them down on paper or you've screenshotted them or something so you have access to them. But if you need some extra time after that 60 minutes is up, take it. Write your questions down and email them to me. If you need more time after the 45 minutes, there's some extra information about how much time you can take and what the maximum score is. Basically, I'll mark it as normal, and then I'll just cap your score. So if you got 95, so if you get 90%, but you submit it 2 hours late, I'll just cap you at 80%. I'm not multiplying by 80%, I'm just capping you at that score. So if you got 90% and you submit it 6 hours late, you just get bumped down to 65. This is just a way to make sure that it's fair to people who do it in the reasonable amount of time. So, I mean, it is a little bit harsh when the time limit gets higher and higher, but nobody really should be taking 12 hours for an exam. If there's extreme difficulties, like there's a medical issue or there's some power outage issue, of course, I'm reasonable. You're not going to be subjected to these lower score penalties. Just let me know. This is for other circumstances. This is just for taking more time or being confused or whatever. Okay, are there any questions about the first test? This is next Tuesday. Okay. I'm just going to switch over. If you have to email the test, okay, so I should clarify. For two of the questions, for the set theory and relations and functions questions, you will have to upload a file to it. So I recommend if you want to type your question, uh, have symbols ready for some of the things, or I recommend using a piece of paper, handwriting things, and taking a photo and uploading them. I don't mind if you handwrite stuff, take a photo with your phone and upload those pictures. There will be an upload file for each question. So for set theory and for relations and functions, or you can upload them all as a unit. I'll put an extra upload file practice thing up there. So if you want to uh, try uploading a file with a photo to see that it works for me on my end, you can try that out. Just for set theory, because sometimes it's a pain to type. And later in the course, we will be doing trees. And I recommend having some sort of setup that you can write with, whether it's paper and pencil or some sort of iPad or anything you can do. If it is Microsoft Word and you do have to just use a typing program, let me know. And I might have to give you some sort of time extension just for working with software, because it is harder to type with that. Okay. So let's continue with propositional logic then. And if you have any questions about the test, of course, you can clarify at any time with me. So there's one term I didn't talk about last time, and that is this thing called a well-formed formula. And basically, a well-formed formula, also pronounced as a woof, uh, is any grammatical formula in logic. So we call these woofs. And this is sort of like in set theory when we said that we had uh, A union B. Like this is a grammatical string of sets, but we can't have something like A union intersection union complement B. This doesn't really make any sense. So a well-formed formula, a woof, is just a grammatical string. One other thing I didn't mention last time is this little thing down here, how we represent our formulas. So usually when we have specific sentences, we use capital letters. So up here where I specified like turbulence is frightening with T or P, and airplanes fly in the sky with Q or A, I use capital letters. But often when we're just talking about random sentences, so we don't actually pick a sentence, but we're just playing around with the variables, we use lowercase letters like P, Q, R, S. And when we talk about like the theoretical stuff, we use Greek letters like alpha and beta and delta and gamma. and phi and psi. And this is sometimes a little bit of a pain at first because there's all these different types of letters and it makes things seem a little bit more formal. This is actually a good thing to get used to because Greek is scary. For some reason, Greek is scary. But again, it's just notation. It's just notation. In the end, it all means the same thing. It's just notation. So when we take a look at this syntax, when we say each atomic statement alpha is a woof in PL, what we're saying here is that when we generate grammatical formulas or grammatical uh, logical strings, we can start with something like P. So we can have this as a sentence. So this is grammatical. We can just have P on its own. And when we start with something like P, which is grammatical, we can modify it to make something else that's grammatical. So one thing we can do is we can say not P. That is grammatical. So that makes a new well-formed formula. If we have two grammatical strings, such as P and Q, we have 4 different ways that we can combine those together to make a new grammatical string or a new well-formed formula. We can take, so let me just show you these. We can do P and Q. So again, I liken this to the intersection. We can do P or Q, and I liken this to the union symbol. I should say that the not P is very similar to the complement symbol in set theory. We have if P then Q, so this is done with the arrow. This is sort of like the subset symbol in set theory. And then finally, we have P if and only if Q. So this is like if P then Q in both directions. And this is a lot like the equal symbol in set theory. So all of these are different grammatical strings in logic. Now, these Greek letters on the left don't just have to be simple. So I'm just using P and Q on their own on the right here, but these can be more complex. So what I mean is, if we have something like not Q and we have something like P or S on the right, we can treat these like, okay, this is an alpha and this is a beta, because these are two grammatical formulas on their own. So this means that I can take 2 grammatical formulas, not Q and P or S, and I can combine them with one of those 4 operators. So I could take and between them, and then I have a new well-formed formula. I have something new that's also grammatical. So this is just a way for us to build grammatical formulas. So we can ask ourselves below, which of the following for 1A, 1B, and 1C, which of those are grammatical? And I want you to take a minute or so to figure these out. I'm just going to make a little poll for these as either yes or no. So please excuse me as I rush on Zoom and create a quick poll for these. Okay, so don't feel like you have to go very quickly, but if you do finish, feel free to put your answers in for which of the formulas are grammatical formulas. What does WOOF stand for again? I'll write this on the top of the page just so we have this here as well. But a WOOF stands for a well-formed formula, and it is pronounced as WOOF. So the first two, or the WF, is well-formed. Okay, so this is going about how I expected, which is always a good thing. So the first one, Q, not P. So not P is good on its own. This is a grammatical string, so we could call this, say, beta. This is grammatical. Uh, that's well formed. Q on its own is fine. That's well formed. That could be our alpha. The problem with this one is that we have two well formed formulas on their own, but we don't have any sort of operator that combines them. So in order for Q not P to be okay, we need something between them for it to be good. So this is not well formed. We need something like Q and not P, or Q or not P, or Q if, or sorry, Q then not P, or we need some sort of operator between Q and not P. It would be kind of like in set theory if we just saw A and then a bracket with B complement. We wouldn't really know what to do with it. You know, you'd be looking at that set and you'd be saying, well, how I know what to do with B complement, I know what to do with A, but how do these interact? So there's a nice parallel there with set theory and logic. So that first one is not well formed for that very reason, is that we need something to combine Q and not P. For B, actually, hold on. I'm going to keep those there because I think that's important. For B, this is good. This is well formed. So what's happening is we have Q, P, and R. And we see that Q and P are together, and they're being joined with and. So this is good. Q is well formed, P is well formed, and we're joining those two together with and to make Q and P. And then we're joining together this well-formed formula and R, which is well-formed on its own. And then we're taking an operator like the arrow, and we're putting those together. So that's also well-formed. So that's good. C, not T arrow, not S. Okay, this is a bit of a mess, but this is also well-formed. And this one is maybe not as intuitive as the others, but we can see how this is constructed. So we have a T and we have an S. And what's happened? Oh, that's covered by my face again, but I need the space. So let's just move me and let's not move S. Okay. So what's happening is we have S. And if we have something well formed, which is just a statement on its own like S, we can attach not to it. And now that's well formed. Okay, so not S is well formed. So we can attach another not to it to make it well formed. So this is like saying we have S complement and we're doing S complement complement. Okay, that's fine. So we can attach another not to it. It's like saying S complement complement complement. We can attach another not to it, S complement 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 complement. And we can keep doing this. Okay, we can keep doing that. I don't know how many there are there. I think that's one too many. Okay. So now we have T, and we have this monstrosity. And we need to combine these two together with an operator, so we do that with the arrow, that's fine. So now this is a well-formed formula. And finally, we can take this whole big chunk, which is well-formed, and we have brackets around this thing, and we can negate that. So in the end, this is also well-formed. So that one's a little bit harder to see because we have this long chain of knots, which seems a little bit unintuitive and unrealistic, but it's still well formed. This is sort of like in English when you see something like, that's not a big, 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 big cat. Like you don't ever see it. It's weird, but it's grammatical. Okay, so
So Trevor,
yes,
so if you, it doesn't matter how many knots you have, it's always going to be well formed.
yeah, yeah, yeah. You can put as many knots back to back as you want.
Okay, so whether there's an even number or odd number, it doesn't matter.
Doesn't matter.
Okay, thanks.
But if there is an even number, you can always simplify things by canceling them out. So we could have just not put any knots there, but we can put as many knots as we want.
Okay, thank you.
Okay, so if this doesn't really click yet, we can also do this visually. So I don't show the visual component right away, but this is another way that we can think about things. So we can think of these in tree structures. So for example, if we have something like P or Q in brackets, we can attach a knot to them and we can get this tree structure above, such as knot P or Q, and that is well formed. So in the example we just had, we could have something like knot, 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 knot S, and we can attach a knot to the right, and that combines to get knot, 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 knot S, and that is well formed. Or if we have, say, some well-formed formula alpha and some well-formed formula beta, such as, I don't know, knot S, and then P and Q, we can combine these three things together to get knot S and P and Q. So we can break apart all of our formulas visually too into a tree structure. And when we think about syntax and how things are put together, maybe as linguists, this resides with us a little bit more. And even if you don't need this, like if you've done this in computing science or philosophy before, you might not have seen this done with formulas. This is actually a really nice way of building truth tables, which we're going to talk about today. It's also a nice way of comparing the structure of logic with the structure of natural language, which we'll be doing in the second lecture, or sorry, the next lecture, when we actually take sentences in English and start building up the truth of those sentences, looking at the meanings of words and building up them into the truth of sentences. So, of course, when we have a binary operator like and, or, if then, and if and only if, these are all going to be ternary branching structures because you have two well-formed formulas on the left and right branch, and then you have some sort of operator in the middle. And I'm always covering that with my face. While the binary branching one above with the not operator will always be a well-formed formula on the right, combined with not on the left. And these are the 5 operators we're going to start with. We're going to introduce one more in a little bit when we talk about or. Okay, so I want to show you this tree diagram with a full formula. So imagine we have this formula, not P or Q, arrow, not S. So we can actually break this down into components and we can see how this is built. So this is important for checking to see if it is well-formed. And if we ever talk about the truth of each of these individual sentences, we can also see how these sentences combine and how the truth is modified piece by piece until we get to the full picture. So that's an advantage that we have later in the system. But for now, our advantage is that we can check to see if this is well formed. So like in syntax, you can always start from the bottom up. So we could do this. We could do not P or Q, arrow, not S. And we could start from the bottom up. And as always, freaking base. Okay, I'm just going to move my head all the way up there. Let's just get out of there. So when we have any atomic formula like P, Q, or S, this is always our starting point. And we have to ask ourselves how these are built. So often I focus on brackets first, and I say, okay, I have P, I have Q, then I have an or in the middle. So I know that these are going to be the first things that join together. So I get P or Q. This is how these are going to be constructed. So this is grammatical. I see that outside the bracket, there's a not attached. So when a not is attached to a bracket, the not is negating the entire bracket, everything inside. So these are joining together with not P or Q, and now this is modifying not P or Q. Okay, so this is well formed. I have not P or Q. I see that there is an arrow here. So an arrow is a binary modifier. So what's going to happen with this arrow is it's going to take a well-formed formula on the left, and it's going to take a well-formed formula on the right. But I don't see anything obvious on the right yet. So I need to start taking a look at S. I see S, I see a negation. A negation is a very powerful binder. It always binds to the thing that's closest to it. So S and the negation will join together to make not S. And finally, I have this second well-formed formula for my conditional operator. So these can now join together, and I get this final well-formed formula, not P or Q, arrow, not S. So the left diagram there is like this top-down structure where I've taken the formula and I've broken it down piece by piece, starting with the whole and breaking it down part by part. And on the right side, I sort of did it in reverse. I started with the bottom and then put it together going upwards. So just like in syntax, you can start both ways, top down or bottom up. I've done the same way with the syntax tree here. Just one was already on the slides, the other one I did by hand. So are there any questions about this process? This is very puzzly in a way. It's just that unlike syntax, in English syntax specifically, there's not really anything concrete to grasp on because you don't have any intuition about an English language to rely on. Okay, so what I want you to do is this one's a little bit tougher. I want you to try this for 2 minutes. Then we're going to take a 10-minute break, and then I'm going to come back and I'm just going to start by drawing this tree out. So I'm going to put 2 minutes on the timer, and then feel free to take a break. And then we'll come back and go over the solution. But if you do have any questions in the meantime, type them in chat or ask me. This one is definitely harder. Okay, if you want to keep working on it, go ahead. Otherwise, we'll take a 10-minute break and we'll go over the answers when we get back. Okay, let's talk about this one. So I'll do top down this time instead of bottom up. So this one uses all of the operators, and this one is much larger, so there's a lot more to do here. But our first step here is breaking up the if and only if, so our double arrow. And that's because we have, if we take a look at our brackets here, we have the negation acting on this large set of brackets, and then we have a negation acting on this other set of brackets. So essentially what we have are two well-formed formulas on each side of this double arrow. So our first step is breaking this up into our two well-formed formulas and our operator in the middle. At this point, we can choose whichever side we want to work on. I'm going to work on the right side first, just because there's a little bit less going on. So the first thing is I have a negation attached to this set of brackets. So I'm going to separate the negation from the brackets. So I can take the not, and then I'm going to be left with S or not Q. At this point, I have a well-formed formula S. I have a well-formed formula not Q, and they're being attached by or. So I can separate those into components. So I'll have S, I'll have or, and I'll have not Q.
Can
At this
we,
point, well, sorry.
sorry, can we put a bracket around S or not Q? Is that
Yeah,
okay?
yeah, that's fine. Usually if you just have brackets on the ends and that's it, we can omit them. So it's optional. So I could have brackets around not Q here too. That's okay. At this point, I just have not Q to deal with, so I can just remove one not at a time. So I get not and not Q. And then I just have not Q to break down, so that'll just be not and Q. So now my right side is broken down and everything here is grammatical. So if I go up the chain in reverse, I can see exactly how this well-formed formula on the right was put together in a way that is grammatical.
I also have a question.
Yep.
For the not Q, can you break it down into three branches and say not, and then Q?
No, because the way that our syntax is constructed, we say that if we have some well-formed formula alpha, we can make a new grammatical formula by attaching not to it. So this is how we construct grammatical formulas. So we don't have a rule that says that if we have alpha, we can take two nots and create not alpha. The system is generated by certain rules, much like in English, we have phrase structure rules that let us create certain grammatical sentences.
Okay, thank you.
So on the left here, it's going to be quite similar. The first thing we're going to deal with is these outer brackets and getting the not separated from those. So we're going to take not on the left and separate it from P and Q arrow R. So I could leave these outer brackets on, but usually we just leave the outer brackets off. At this point, we can see we have we have P and Q as a unit, and we have R as a unit, and then we have this arrow joining them together. So we can break these up into three components, P and Q. We can have the brackets on if we want, arrow and then an R. We can't break down R anymore. We can't break down the operator anymore, but we can break P and Q down into P and Q. So this is the tree structure for this syntactic tree. And again, if we go in reverse from the bottom to the top, we can see exactly how we took all of these individual pieces and put them together using our syntactic rules for propositional logic to create this complex formula at the top. So are there any questions about this process or any places that you did it differently or struggled with? Exactly same as you did. Okay. I asked because I know that the syntax of propositional logic goes in sort of two ways for people. For some people, this is like very simple, very boring, and for other people, this is moderately difficult. And the reason I harp on this is because it is important structurally for what we're doing in the future with syntactic structures and also for truth tables, which is about what we're just going to jump into now. So taking the time to understand how these formulas are put together is highly advantageous, and it's something worth taking the time to understand. Okay, so logic really isn't just about the structure of these well-formed formulas. The point of logic is about truth, like I said at the very beginning of, or sorry, at the very end of Friday. It's about taking English sentences and analyzing whether those sentences are true or false. That's going to be the goal of propositional logic in our system. So, uh, in logic, we have these things called truth tables. And what truth tables do is they track all possible configurations of truth. So, this means that in every possible universe or situation, we can determine whether a well-formed formula is true or false. So here's sort of like this abstract example. Imagine we have two well-formed formulas, alpha and beta. So these can be simple sentences, they can be complex sentences, they can be whatever sentences we want them to be. And it doesn't matter what sentences these are, but we want to know all possible configurations of truth. So we want to know what happens when alpha is true and beta is true, for example. So this could be one situation. And normally we would call this something like B1 for situation one. For some reason in semantics, we use a V for situation. It's just something we do. So we represent this by saying that alpha is 1 and beta is 1. So remember that 1 means true in our system. So one line says alpha is true and beta is true. That's one situation. We have another situation where we want to track to see what happens when alpha is true and beta is false. So alpha is true and beta is false. So remember that in our system here, 0 means false. So that's another situation we want to track to see what happens. What if alpha is false and beta is true? So this might be situation 3. So in this case, alpha is false, beta is true. So alpha is 0, beta is 1. And then in situation 4, what happens when both of them are false? So alpha is 0 and beta is 0. Okay, so what this truth table is going to do is when we combine alpha and beta in different ways, it's going to track in each situation to see what happens to the truth. So if I am happy and I have brown hair, if I put those two sentences together, what happens to I am happy and I have brown hair if both of those independent sentences are true? What if just one of them is true? What if both of them are false? How does the truth of that compound sentence change depending on each of those situations? That's something that a truth table does. So here's some general facts about truth tables. We have these things called atomic statements. This just means something like alpha. So if we have a truth table with just alpha, we're just going to have 2 rows in it. So we'll just have rows with 1 and 0. We just need to check 2 possible configurations. If we have 2 atomic statements like alpha and beta, we're going to have 4 rows. We need to check all the situations where alpha and beta are both true, alpha is true, beta is false, alpha is false, beta is true, and alpha is false and beta is false. You might notice a similarity here between this and power sets. There's no coincidence here. If we had 3 atomic statements, alpha, beta, and delta, then we would need 8 rows, because we'd have to figure out when alpha, beta, and delta are true. Alpha, beta is true and delta is false. Alpha is true, beta is false, and delta is true, and so on. So it's very similar to a power set. It's constructed in pretty much the same way. The more atomic statements you have, the more different possible configurations of truth you can have. So if you ever have to do a truth table in this course, you'll never have more than 3 different sentences you have to look at. Otherwise, the truth table just becomes too big. There's one little bit of notation too. If we ever want to write that the value of some sentence or a statement is true, we use square brackets. So here I just wrote like alpha equals 1. Really, I should be writing this in square brackets. So I should be rewriting this as, say, the value of alpha is 1, the value of beta is 1. The value of alpha is 1, the value of beta is 0. So this is just read as the value of. So that's what these double square brackets mean. And you can just write this as like 2 left brackets back to back. That's usually the easiest way of doing it. If you use LaTeX or some other program, there's a special command for it. I think I have it on the discussion board on Canvas as a shortcut in the list of typing symbols. Okay, so truth tables are about tracking truth. So with atomic statements, we initialize these with all possible truth values. But what's more interesting is how truth values change with operators. So what we're going to do today is basically look at all the different operators and see how truth values change when we attach operators to them. And we're going to take a look at examples in natural language. So that way we get an understanding of how those truth values work and actually get some concrete examples and some intuitive understanding as well. Well, hopefully get some intuitive understanding. And as always, like, interrupt me anytime you have questions or type in chat and I'll answer you. Okay. And like set theory 2, we're going to have some formal definitions, but I'm just going to try to explain these in as natural terms as I can. So the first one is the negation. So this is when we have some formula alpha and we attach a negation symbol to it. So in English, we usually see these terms as in not, or it is not the case that, or it is not true that, or it does not happen to be that. Usually the word not is in some sort of phrase. And what happens, and I'll try to use colors for these too, is that if you have a truth value, like 1 or 0 in your original sentence, alpha, what the negation does is it flips the truth value. So if alpha is true, or 1, then not alpha will be 0 or false. If alpha is false, or 0, then not alpha will be true, or 1. So it just flips the truth value. And this happens in natural language. So if you have some situation in the world where Josephine is sleeping, and we say, is Josephine awake? Well, or we have a sentence, Josephine is awake. Well, that's false. You know, if Josephine is sleeping, then Josephine is awake is a false statement. But if we negate this, so this would be alpha, and we negate this and make it not alpha, Josephine is not awake, then that suddenly becomes true. Because if Josephine is awake is false, then Josephine is not awake must be true. Here's another example. if we say the sky is blue, I can't really see, but let's just say this is true. If we negate this and say the sky is not blue, then we're negating that sentence. So if the original is true, then the negated version must be false. So the negation is going to flip the truth value of whatever sentence you have. This can be a simple sentence or it can be a complex sentence. It will just negate whatever you have. So this is the simplest operator that we have because it just flips the truth value. I do just want to emphasize that one point that I made and just illustrate it. If we have something, I'll just replace it with the alpha here. If we have something like P and Q, and we replace it with not P and Q, we get the flipped truth value still. This is what I mean when we say it negates complex sentences too. I just want to make sure that point is illustrated because I have seen confusion about that in the past in truth tables. So just to illustrate that. Okay, so that's our only unary operator. So we just need to take a look at one thing there. So we just need to take a look at one column. The rest of these operators are binary operators, which means we have to compare two truth values. So something from alpha and something from beta in order to get our new value. So we'll start with and. The conjunction. So this is our caret, which in set theory is a lot like the intersection. And our stereotype word or our prototypical word is and. But this is pretty much any conjunction except for or unless. So, but, although, yet, so, therefore, however, in addition to, pretty much any conjunction in English is a conjunction in logic. So I'm just going to write except for, or, and unless, and conditionals. So conditionals might be a little vague for now, but a lot of the conjunctions in English are actual conjunctions in logic as well. And what is a little bit confusing is that when we say conjunctions in syntax, we do mean something slightly different than when we say conjunctions in logic. Conjunction in logic specifically means and, while conjunction in syntax just means like a connecting word. So there is a difference there. Syntax, connecting word, logic, and. So when we talk about conjunctions in this course, we typically mean and, unless we talk about it in a syntactic environment, which I'll try to be specific when I talk about conjunctions in syntax. Okay, so how and works. And compares two things. So we need two well-formed formulas, alpha and beta. And so let's just draw two truth tables here. Let's use colors. And alpha and beta is going to be true when both alpha and beta are true. It's going to be false in every other case. So in this first situation where alpha is true and beta is true, then alpha and beta is true. Like the trees are green and the sky is blue. If both of those are true, then the trees are green and the sky is blue is true. But if I say the trees are green and the sky is blue, well, if the trees are blue, then the conjunction's not true. Or if the sky is gray, then the conjunction is not true. So in all the other cases, this will be false. So it's false in the second line because not both of them are true. It's false in the third line because not both of them are true. and it's false in the fourth line because neither of them are true. So in our situation down there, Josephine is sleeping and Brett is humming. So we have our sentences here. Josephine is sleeping. Yeah, that's true. Brett is humming. That's true. So because both of those individually are true, we can say Josephine is sleeping and Brett is humming. Therefore, that's also true. And that's because we have 1 and 1. But if just one of those were false, then the conjunction would be false. So this is probably the most straightforward binary operator because this, goes along with our expectations. It's like if you went to someone's house and they said, yeah, you can have cake and ice cream. And then you got cake and they said, sorry, you can't have ice cream. You would probably slap them across the face and call them a liar because they said you could have cake and ice cream. So why can you only have one? You would expect that you could have both. So if they say X and Y, you expect that you should have both. Now, some of you may be thinking, hold on a second. And, but, although mean slightly different things. So why is but included as a conjunction and although included as a conjunction? Because don't they mean different things? And the answer to that is yes. However, this is slightly outside the domain of semantics. So I want to illustrate this, but the overall point is that this is not necessarily semantics. Some of this stuff is pragmatics. Remember, semantics deals with the literal language aspect and pragmatics deals with expectations about language and conversation and real world knowledge and so on. Yes. Sorry, is there a question?
Oh, sorry, I just unmuted myself.
Okay. Okay. So, one example with and, for example, is that and sometimes implies a sequence of events. So this is an example I like to use because this is like rooted in society. So this is an example that, evokes some sort of response with everybody. So Megan got married and got pregnant versus Megan got pregnant and got married. So this is a little bit more traditional, but usually it evokes a response so I can make sure that I can get the implicature from everybody. So usually we don't just infer here that there are just two facts. Usually we infer that there's some sort of sequence to this. In the first one, we expect that there is a marriage first, and then there's a pregnancy, while in the second one, we infer that there's a pregnancy first, and that's what caused the marriage. So if we think about something that happened in, say, the 1930s in North America, you know, that this is very culturally relevant to the 1930s, 1940s, 1950s, even up to the 80s, really. So this is an inference, but this isn't something that we include in our semantics. We just care about the truth of what happens with and. If we have fact A and fact B, and both of those are true, then what happens to the compound of those? We don't care about the time sequence. We don't care about our expectations. We just care about the literal language. So there is an inference there in some cases, but not all, but that's not our worry. We also have cases with words like but and even though. So sentences like Jane snores, but John sleeps well. Even though Jane snores, John sleeps well. These words have contrast to them. Like, it's surprising that Jane snores. Or sorry, it's surprising that John sleeps well, even though Jane snores. And there is contrast to these. If we said Jane snores and John sleeps well, and we compare that with Jane snores but John sleeps well, there is a difference in meaning. But again, this is not our concern to deal with contrast in semantics. What we're concerned about is with truth. In lexical semantics and in pragmatics, these are important distinctions. But for us, who are going to be dealing with truth conditional semantics, In the end, when we think about the meaning, Jane snores, but John sleeps well, with the facts of the sentence, is it true or not? The sentence is only going to be true if this fact is true and this fact is true. We can still say the sentence is false if one of those facts is not true. So all these little extra meanings that we get from words like but, although, even though, however, we don't have to worry about these. So I bring this up because I know that sometimes when you're working on these problems and you come across these words like although and even though, you're going to be thinking, what sort of operator is this? And you'll think, okay, there's contrast here, there's not contrast and what is this going to be? So don't worry about that. Just think about how the facts are connected to each other. What are the conditions for the facts? But there's certainly a lot to talk about here in both lexical semantics when you talk about the meanings of operators and really break into what a word is and what makes up a word, and definitely in pragmatics, like when these words are used and how these words are used and in what situations and what the meanings implied by these words are. So I'm not saying they're not interesting. I'm just saying for our purposes, we don't get to dive into them. Okay. We got 4 more operators. We're going to talk about or, and we have a distinction between 2 different types of ors, and this is where things can get confusing to people. So we're going to start with something called inclusive or. So inclusive or in English are words like or and unless. Now, inclusive or, we just set this up. And I'm just going to copy and paste this for convenience with colors. Okay. So inclusive or. Inclusive or is true. So this requires 2 well-formed formulas again, alpha and beta. Inclusive or is true if either alpha or beta is true, or both of them are true. So one way I like to think about this at first is at least one of alpha or beta is true. So when we put these together for alpha or beta, this is true in the first line when both alpha and beta are true. It's true when alpha is true, but beta is false. It's true when beta is true, but alpha is false. But it is false in the case when both alpha and beta are false. So if you have some situation where Josephine is sleeping and Jack is sleeping, and we ask a question or we have some statements like Josephine is sleeping, that's true. Jack is eating, that's false. And we ask, is Josephine sleeping or Jack eating? Yeah, we can say that's true because at least one of these 2 things is true. Josephine is sleeping. So yeah, this or statement is true. Okay, so this is called inclusive or because this first row is true. It's inclusive or because it can be true when both alpha and beta are true. So this is like asking someone, so imagine you have a student who's taking LING 100, LING 220, Math 151, and I don't know, like Essay 150. And you ask them, are you taking LING 220 or Math 151? So this would be an example of inclusive or. Now, how would you expect that student to respond? You would expect them to say, yes. Are you taking LING 220 or Math 151? Yeah. You would expect them to say yes. So this is an example of inclusive or, because yes, they're taking both LING 220, that's true. They're taking Math 151, that's true. So they're taking at least one of those. If you were to change this and you were to say, or fill 100. Well, maybe I should use a different color. Maybe I should actually use green for that. Well, you'd still expect them to say yes because they're taking LING 220. So in both cases, whether you ask them, are they taking LING 220 or Math 151, where they're taking both, or are you taking LING 220 or Fill 100, where they're just taking one, you would still expect them to say yes to this question. So that's why we say that in English, or is an example of inclusive or, where you can say it's true if either alpha or beta is true, or if both of those are true. If we asked, just for the sake of completion, are you taking LING 160 or Fill 100? In this case, they're taking neither. So then they would say no, because they're not taking either of those. Okay. You might ask, hold on a second, how is unless inclusive or? This is a little weird. And to be honest, this is a little weird, and I don't have a nice way of explaining how this is unless. The only thing I have to say about this is that unless is used to describe this monstrosity, which is not P then Q, which is a short form for P or Q. So unless is really just a short form of or that happens to work for a more complex form of English. So although unless intuitively doesn't work as or, it has the same meaning as or. Unfortunately, I just cannot explain in natural language how that works. I don't quite understand how to explain it in natural language, but I will talk about it in the conditional at some point. This is just one of those things I have memorized that makes life easy. But I can explain that in terms of the conditional at some point. So I'm sorry for the unsatisfactory explanation of unless at this point and why it's inclusive or. It's just a shorthand for or. Okay, now we got to talk about the other type of or. Oh, sorry. We've done a few operators, so I should pause for a second. Does anyone have questions about the operators we've covered so far? Okay. Okay. Exclusive or. So English doesn't have an individual word for exclusive or. In order for exclusive or in English, we have to specify it explicitly in semantics. Otherwise, it's an implicature. It's an expectation. So if we want exclusive or to actually be translated, we have to say something like, I want A or B, but not both. Or I want exactly one of A or B. So how this is described is we say that A exclusive or B is true if and only if the values of alpha and beta are not the same. So how this looks like in a truth table is as follows. So we can set up our truth table. So this is the same thing as inclusive or, except it is false when both alpha and beta are true at the same time. So it's called exclusive or because you can only have exactly one of A or B, exactly one of alpha or beta. So this is A or B, but not both. So in English, we don't actually have a word for this. This is just an expectation. So one example that is typically given of exclusive or is what's shown in 7. When you go to a restaurant and you see a sentence, all entrees are served with soup or salad. And there's an implicature here. The implicature is you can only have one of the soup or salad. You can't have both. And although this might be true at a lot of places, this is something that has to be verified. So there are many restaurants where you can have both. You might have to be charged extra for it. There are some places that will actually give you both for free. They're not very common, but there are places that will do that. But you have to ask, you have to clarify. We don't just have an or that is exclusive on its own. So in this course, we will not be translating any sentences with exclusive or unless it explicitly states, but not both, or says exactly one of. So just be careful when you see sentences. The typical default is just assume it's inclusive. Exclusivity is part of pragmatics. It's part of implicature. But just to make you aware that exclusive or is something that exists, and typically in computing science, discrete mathematics, this is something that's a little bit more common than it is in the discussion of English semantics and English syntax. Okay, so we'll finish off our discussion today with the conditional and the biconditional. And these two, I'm always afraid of talking about these two. The conditional is always a mess to talk about. And in psychology, there are many studies on the conditional. I'm sure some of you have heard about the study of the cards with AB47. And I moved my camera to the top. So AB47. There's a thing that says if there's a vowel on one side, then there's an even number on the other side, and these are cards, and then people are asked to flip the cards to verify whether that statement is true. And they do this test on children and adults, and people are just very bad at it. And that's because people are bad at conditional reasoning. That's the general finding of conditionals. So when we talk about conditional logic, it's no surprise that people are also they struggle to grasp it when they first learn it. So if you struggle with this, it's normal. It's psychologically proven that it's difficult. So it's always scary to teach it too. Okay, so conditionals. This is an if-then sentence. Basically, let's talk about some terms first. So alpha, then beta. So we have some terms here. If we have alpha arrow beta, I usually just call it arrow instead of if then. You can call it an arrow too. On the left, we have what is called the antecedent. So this is the condition. This is what has to happen. This is the if part. So antecedent, you might have heard this term in syntax too. Typically, the antecedent is what gives meaning to some other word. So Stephanie said that she went out. Stephanie is the example of the antecedent for she. Stephanie gives meaning to she. This is sort of the same thing. This is the condition for what has to happen for beta to happen. So this is the antecedent, that's alpha. B is what's called the consequent. So this is what happens when the condition is met. Okay, so how this works, how the conditional works. Is that if the condition is true, if the condition happens, then the consequent must happen too. So here's the example I'm going to use. If you eat your dinner, you can have dessert. Okay, so imagine you ate your dinner. That means that you can have dessert. So if alpha is true, then beta is true. So this is a true circumstance. So then alpha arrow beta is true. But imagine you ate your dinner and then suddenly your parents say that you can no longer have dessert. They told you originally, if you eat your dinner, you can have dessert. You ate your dinner, but suddenly you can no longer have your dessert. This is problematic because essentially your parents have lied to you. If the antecedent is met, and you're saying there's a conditional, if the antecedent happens, then the consequent happens. Uh, if the antecedent happens, the consequent should happen. Therefore, this is going to be false if the antecedent happens and the consequent doesn't. So the second low where alpha is true and beta is false, we end up with alpha arrow beta being false. So in other words, you can think of the conditional operator being false when you're being lied to in this circumstance. So you're given a condition, you're given a consequent, the condition happens, and then the consequent doesn't happen. If that scenario occurs, you've been lied to, therefore the entire conditional is just false. Are there any comments or questions about that row? Okay. The other situation below, the other example. Imagine I say, if it is raining, then it is wet outside. And it happens to be raining outside, but it's not wet outside. Then the fact that I say, if it's raining, then it's wet outside, this is false because essentially I've made sort of a lie here. I'm saying, if it's raining, then it's wet. Well, it's raining, but it's not wet. Well, then my conditional happens to be false because what I've said, if it's raining, then it's wet. Well, it's raining, but it's not wet. I've lied in that case. So it's false. Okay. So maybe that part's not too bad. The next two parts are a little unintuitive. If the antecedent is false, so imagine I say, if you eat your dinner, you can have dessert, and you don't eat your dinner, it doesn't matter what happens to the consequent. The conditional is automatically true. So that might be a little bit unintuitive, that the conditional is automatically true. And the idea here, the sort of intuitive idea here, the explanation that I've always gotten, that makes sense sort of in my head, is that if we think about this in terms of it being false when we're lied to, is that if the antecedent or the condition is false, we cannot test the conditional. And because we cannot test the conditional, we cannot claim that it is false. We cannot claim that it is a lie. So because we can't claim that it's a lie, we cannot test it. We assume that it's true until we have evidence that it's not true. So whenever the condition is false, whenever the antecedent is false, we just assume that the conditional is true. So if I don't eat my dinner, I can have dessert, or I cannot have dessert. It's up to me. Okay, are there any questions about the conditional? Okay, we have just one more, and then we're done with all these different operators, and then next week we'll get to put them together and put them to use. So we can come back and talk about this example next week if we're having some difficulties with the conditional, but this basically just explains that if the antecedent is false, then the entire statement is true. Okay, so this last one is the biconditional. So this is this double F we've seen. So if with two Fs, this just means if and only if. So I've said that A arrow B is like if. So there's this only if operator, and this means something different than alpha arrow beta. So on your next assignment, I believe you have to figure this out. I'm not 1000% sure. I modified it last night, but I can't remember if I left the question in or not. The goal is for you to figure it out. But A if B, A if and only if B, is the conditional in both directions. So that's a major hint of what only if means. Another way of thinking about the biconditional is A is the same as B. And how we can think about the biconditional is saying A arrow B and B arrow A, or alpha arrow beta and beta arrow alpha. So what we end up with is the fact that it's true only when alpha and beta are the same value. So when alpha is true and beta is true, and alpha is false and beta is false, and then alpha if and only if beta are false when alpha and beta have different values. So this is very similar to the equals in set theory. So, A equals B is the same when they have the same elements. So in logic, this is like when they have the same truth values. And A equals B, well, they're not equal when they have different elements. So the biconditional is false when they have different truth values. So there's, again, a very strong parallel here between set theory and logic. So, for instance, Z is a number if and only if 3 is a letter. So this is a true statement because Z is not a number. 3 is not a letter, and this is the biconditional. So because we have 0 if and only if 0, this whole thing comes out to be true because these are both the same truth value. Z as a number is false, 3 as a letter is false. They both have the same value. This is an if and only if statement, therefore the output is true. Okay, so I know going through all the truth values of different things can seem like a lot, especially going with the English equivalents of words. But on Friday, what we're going to do is we're going to put them together. We're going to see how to build truth tables using these different operators, how to do a syntactic tree and a truth table all at once. And then we're going to learn how to translate English sentences into propositional logic. So that way, eventually what we can do is we can take English sentences, we can convert them into these logical formulas, and we can talk about all the different situations and those truth values. So when we have, like, say, a short paragraph, we can see what happens to the truth as the sentences get more complicated than complicated. So eventually we could have, say, an argument, and we could see what happens to the argument as it gets more complex, and to see if an argument actually entails a conclusion or not. So, I mean, that's something that would happen in a philosophy course, but that's something that you would have the capacity to do in this course if you were to go that far. So anyways, that's it for today's lecture. If you have any questions, you can stick around. Otherwise, yeah, that's it. I won't be releasing assignment number 3 today because I'd like to give you a mental break from everything, but I will release assignment 3 on Friday. Remember to get those practice exercises done if you haven't had them done yet. They're due on Sunday. I think that's everything. If you have any questions about the test, as always, email me, discussion board, all the regular stuff. Bug me as much as you need to bug me. And yeah, I'll see you Friday.
Thank you so much, Trevor.
Ah, no problem. Enjoy your week.